Welcome back. This is Glenn again, and I'm going to talk to you about convergence for the free elastic flow supported on parallel lines. So let's get into it. Now, what we saw last time was that once we gained some control on a derivative of curvature, in particular, last time for the curved diffusion flow, it was the second derivative of curvature in L2. We proved that that decays exponentially fast under our curvature condition. Once we obtained that result, then the rest was fairly straightforward. And for free elastic flow, it will be the same, but we do not proceed the same way in the beginning. Okay, free elastic flow. Okay, so we're doing convergence, and first, before we obtain... Okay, so also we should just keep in mind that our condition is a lot stronger. It's a lot better, it's a lot better condition for the free elastic flow than for curved diffusion. We can go all the way up to pi. And so we have to be a little bit more, and we really want to include this equal line. That is, there's no reason to get rid of it, so we can do it, so we will do it. The first claim is that we have the curvature in its supremum norm converging to 0. Okay, and to do this, we are going to leverage the, we're going to combine this curvature condition with the gradient flow structure of the free elastic flow. So it's going to become actually relevant, the fact that it's a gradient flow, again, relevant again. Okay, so first thing to note is that this quantity is either strictly decreasing or 0. Why is this true? Now, I'm not going to write down the argument for this because it's an elastic argument. I will say it though, so you know. Again, this is a little bit like, destroying a hill with a nuclear weapon, but or a sledgehammer. I was using the word sledgehammer before, but still it works, so we can do it. Because of the we have a full classification of elastica, and in particular, we know all the elastica that satisfy our boundary conditions, and those are the rectangular elastica with a multiple of half periods. So you can have 1 half period, you can have 74 half periods, whatever you like. The smallest amount of curvature is when you have just 1 half period. And the amount of curvature that is used is pi squared. It's not, I mean, it's more than pi squared. It's an inconvenient constant bigger than 1 times pi squared. So in particular, because of our curvature condition, there is not even a half period of a rectangular elastica. The only elastica that you can have is the straight line. So that means that at each point in time along the flow, either we have strictly decreasing, like this quantity is either strictly decreasing, or if it's equal to 0, then actually we are already on a straight line. Okay, so that's the conclusion from that little argument. You can also make the same conclusion. You can also obtain the same conclusion by using an analyticity argument. Because the flow is analytic in time, it can't actually reach any kind of equilibrium in finite time. So it has to be strictly decreasing, for all t. Or just 0 from the beginning. So what this means is that it basically means that there's the equal to pi part is not a problem. It means that there is a delta such that for t bigger than t0, which is bigger than 0, we have L times K in L2 squared smaller than or equal to pi minus delta. So there's an improvement. Okay, there's a slight improvement. Now, the fact that we have an L2 gradient flow for the elastic energy implies that, well, it means really that E prime, which is, by the way, the double of this quantity, is minus the F for the free elastic flow. I should write down what the F is. F is KSS plus 1/2 K cubed in L2 squared. And this is at each t. And now you can turn this around and get some control on the time integral of f from this equation. In fact, you can integrate from 0 to t for any t. This quantity, which is of course a quantity that depends on time. And you get the energy at time 0 minus the energy at time t. So in particular, what you can do is take t to infinity, and this is just a positive thing, and turn this into a less than or equal to, like that. My God. Glenn, just rub it out. Less than or equal to infinity. And you get this type of statement. And now what you've got is a function that is non-negative, exists on 0 to infinity. Its integral is finite. That means there's a subsequence of times along which it goes to 0. However, because of our bounds for all the derivatives of curvature, we actually have, just in our back pocket, that the time derivative of this quantity in absolute value is bounded, right? Because all this is a collection of derivatives of curvature all multiplied together. It's all bounded, so this is bounded uniformly by our previous arguments. And so then this means that this quantity actually has to converge to 0. In t. Okay, so that's the first part. That's a nice little independently interesting thing, but we're not finished. Because, you know, that's sort of generically true for pretty much any kind of gradient flow. What we really want to do is get more information than that. We want to say that it means that the curvature is becoming small, and we need to use the particular structure of f to get that. Okay. All right. So what we're going to do is test the speed with k. So the integral of fk, we actually saw this before when we were doing the derivative of length. So L prime is also equal to this. This is this quantity by integration by parts, and then you also have here this one. And now we're going to do a calculation that's analogous to what we did before, but now we have a lot more, but now we have a trick up our sleeves, because the trick up our sleeves is that this is becoming 0. Because, why? Because this thing itself is bounded using the Hölder inequality by f in L2 at time t times k in L2 at time t. This thing is bounded, this thing is converging to 0, so this whole thing is going to 0. That means that this is going to 0. Okay, but now we can do our standard sort of estimate to control this term in terms of this one. And we're going to find something interesting. Okay, 1/2 times k L4 L4. Okay, we use L infinity. We're going to take out 1/2 k in L infinity, and then that's going to be multiplied by k in L2. And then we're going to use, because we have just k by itself, we have to use the Poincare, which means we pick up a 2, which means, by the way, that this 1/2 is crucial. If this 1/2 was not here, the result would not work. So we're going to get a half 2L over pi. There's a square here. And then this is going to be k s. Oh, sorry. I think I made a typo. Yeah, here. Sorry. Also, why? Oh. Sorry. Maybe that was supposed to copy and paste, not just... Did that disappear randomly later? I'm not sure. Anyway, whatever. It doesn't matter. That's that, and that means that goes to 0, and then we use the L infinity. We have this in L2. Okay, which is that one. That's how come I realized that there was a typo, because it was SS here for some reason. I just made a mistake. And now we've got this in L2, which is going to combine with the L. So anyway, we'll just write it down for now. Okay, and now this is going to make 1 over pi. And this is L. So this is L, K, 2 over pi. And now you see what happened. Something very interesting has happened, because the fact that this is decreased means that if you're bigger than this time t0, then you actually get pi minus delta here. Okay, so this is 1 minus delta over pi times ks 2. Which is pretty powerful. Oh, this is for t bigger than t0. Because here you've got the -1 here, so that'll cancel out with this one, but then you're still going to be left with a ks. And so that means that this, combined with this estimate, gives you delta over pi times ks going to 0, or simply ks in L2 going to 0, which then gives you, by the Poincare inequality in L infinity, the fact that the curvature goes to 0, which is what we claimed. So that's great. So that's a really powerful first step. We now have the curvature going to 0, but we have not been able to pin down the rate of decay. And that is crucial, because without the rate of decay, we can't do our standard argument to prove that the position vector is Cauchy sequence, for example. And in general, it's not true. So you can have gradient flows and evolution equations where the velocity decreases and goes to 0, but the actual equation does not converge. That can happen. So just because we showed that that the curvature goes to 0, that will also imply by our earlier estimates that all the derivatives then also go to 0. We don't have any control over the rate, so we're still not done. We're not exactly done yet, but we sort of are done, but anyway. Okay, so what do we do next? We're going to go back. It's always the same story with this gradient flow. We're going to go back to the structure of F. And this time we're going to look at the square. So just a second ago we studied the testing the F against the curvature. And we obtained a nice result. And now we're going to look at estimating the square from below. So we're actually testing F with itself, which is a standard thing to do. So this is a square. You can calculate what it is. This time you're going to get KSS squared. And then the cubic term, square it. You're going to get a quarter times K in L6. And then you're going to end up with another term, which is the cross term, which is going to be this. Okay, and now this one you can integrate by parts and get -3. Use the no flux condition. Ks squared K squared ds, like that. Okay, and we want to estimate this from below. So this is bigger than or equal, and we can do this pretty crudely because we already have that curvature is becoming small. So a crude estimate is totally fine. So in particular, we can just throw away this term and just focus on the diffusion term. Basically, this makes sense because what's happening is that when we get into these large time limits, once we have our foot in the door, which we've already got, we're basically going to lean on the diffusion terms. So you're going to see a lot of intermediate terms just be thrown away because it's not important anymore. The big thing has already happened. Okay, so we're estimating from below, -3. And we can take the k out in L infinity, and then we can estimate the ks squared using Vertinger to get it in terms of this one. And so that's what we'll do. So we'll take this out in L infinity squared, and then the price we need to pay is a constant. It's going to be pi over L. Pi squared over L squared. Oh, sorry, L squared. Pi squared over L squared, I think. Sometimes, just a second. Sometimes my brain needs calibration. So the right and when I'm estimating things from below, it can get confusing. So do it this way. You have L squared over pi squared KSS. Okay, so yeah, so to go the other way around, you need to, oh no, it's just L squared over pi squared. Yeah. So minus that, yeah, is greater than or equal to minus that. Okay, no. It's L squared over pi squared. Sorry, I'm just a bit slow sometimes. L squared over pi squared, and then I've got this guy again. Okay, but you can see what's happening because we're going to have 1 minus, and then this is going to be this is uniformly bounded, and so this is going to be a function that goes to 0, so some f of t. It's going to 0. And then you're left with this. Okay, and now this is really good news because we can use this with the evolution of the energy. So we'll go back to the energy now. So we're using all of it. So this is going to be exponential decay of the energy. Right? because, so E prime of t is minus, and then you've got this L2 norm of f. And what we just showed was that f was bounded from below by 1 minus this thing that goes to 0 times KSS squared. Thing that goes to 0 times KSS squared. Okay, but now this E, by the way, is just 1/2 K. But this can turn into exponential decay really easily. So just take, say, t bigger than t1, where f of t is less than 1/2 for t bigger than t1. So what we've got is k to 2 prime smaller than or equal. Now this is going to be minus 1/2, but there's a half on the left, so it's just a minus. And now what we do is our usual tricks. We're going to estimate this using k, because we can go, usually we go up on the right, but this has got a minus, so we go down. And we're just going to pick up a constant. Like that. Right? And this constant will be pi to the 4 divided, no, 2 pi to the 4 divided by L to the 4. That's what it'll be. But anyway, it's a uniform constant. And this equation is our exponential decay. So exponential decay in the curvature itself, in L2, which is the energy. So the energy is decaying exponentially fast. Okay, that's it. So this is the main thing. That's actually the main estimate. And then once we have this done, then we can proceed exactly like before. So now that we have, there's a slight issue. Okay, so you might ask me a question. Hey, Glenn, this only works after T1. So after time T1. What about before? Well, I'm glad you asked. Your check is in the mail. So say we've got, this is our time, this is t. This is t. And let's take, I don't know, let's look at just the curvature in L2. Okay, then who knows where this time is? It's some time, T1. After T1, it reaches a certain value, whatever value it is, it's finite, because we know everything is bounded uniformly because of our work before. Because of Chuk-Kubert-Schätzler, everything is bounded already. And now once you get to here, that's when the exponential decay kicks in, and we know its decay rate. So this is exponential decay. Up until that point, well, yes, there's a bound, but who knows? It could be doing, well, it can't do that. Let me just not be so crazy. So it could be up and down, I don't know, like that. In this picture, it kind of looks like, yeah, this is not a great picture because I want to make it as bad as possible. Let's say, well, this, oh my God, I'm failing to draw this picture. This quantity can't actually go up because this is monotone non-increasing quantity. So my God, Glenn. So yes, it could go down slowly and then quickly and then slowly, whatever. And let's say it goes down really quickly here and then whatever. And maybe its true value is down here. I don't know. Now what can you do is just multiply this this area. So this curve that's bounding the decay rate, just multiply it by an appropriately large constant. I can tell you which constant to pick already. Just pick the constant that makes this up here, that brings this point to here. because you already know that it's going to be below this area down here, so that's definitely going to bound it from above. And in this region, you have this estimate already. And this green curve, this exponential curve, will be up here. So what it means, it doesn't matter. It does not matter that you have to wait until T1. You still get exponential decay. It's because all the interesting behavior is happening in the tail. That's why. So as far as you go along, eventually the exponential decay will just crush it down to 0 very quickly. Okay, that's one natural question. So you have exponential decay, and then you just proceed as in the previous argument. So here's the previous argument. I'm going to write in green. So we don't have KSS, but we have K like this. And so we use the same argument. So we estimate this using either Poincaré or Wirtinger, depends if L is even or odd. And then do interpolation with integration by parts. You don't need to do anything too fancy. And use the decay of the curvature to get this. So all the derivatives are decaying exponentially fast in L infinity. And then you do a similar thing, same thing actually, exactly the same thing. You just integrate the flow equation. You have exponential decay on the speed. So you get a Cauchy sequence. You can get existence of a limit, which is going to be a straight line because of all of these estimates. And that's it. That's the end. We proved it, finally. Okay. So just to wrap up, I just want to give a couple of open questions. I know this video is very long, and I thank you for your patience, but I don't think it's worth making another whole video for just a little bit of information. So I'm just going to stick it here, and then I'll thank you for your attention and for your patience. Okay. So here we go, 2 open problems. As you can probably tell, this is new stuff and it's not sharp in any way. Almost everything that I've talked about can be done better. This is just a foot in the door. This is just the first thing. So definitely the big thing is to improve these constants. And I'll just say it again. I've said it before, but the convergence result should hold now. Typically the curved diffusion flow is not as well behaved as the free elastic flow. So for example, if you have curves with no boundary, then the free elastic flow always exists for all time, and it'll make the curves get really large. That's in Chuk, Kuvert, and Schätzler's paper. Whereas the curved diffusion flow does not have that property. It doesn't have that nice behavior. It actually has singularities. We found this lemniscate of Bernoulli that will shrink to a point in finite time. And then there are other examples like Meyer's curve, which is initially an embedded curve that becomes first immersed, and then a loop pinches off and singularity. Now that's not proved rigorously, but it is established numerically. So we have to be a little bit careful about our conjecture here. Nevertheless, I think it's fairly safe to say that it should hold when this quantity is less than or equal to pi. So I think that's true, but I don't know how to prove it. There are sort of 2 ways to go about this. Anyway, I'll talk about that in a second. For the free elastic flow, I think the corresponding conservative conjecture is that it can be pushed up to pi squared. So our result at the moment has this number to be 2 pi over 9, and this number is pi. So that's quite a significant difference to what we're saying should be possible, should be safe. And there are 2 ways to go about doing this. So one way is to just do what we did, but better. Do a smarter estimate, you know, there are some terms that we threw away. Maybe you can estimate those in more precisely. And at times we did not use a product structure. Instead, we estimated each term individually. So those are the two things that I would focus on improving. The other way to do it would be to come up with a different idea. So, for example, you might like to think about what happens when you don't have convergence, and then you have blow up, and what sort of singularities can you actually get? Maybe you can't get singularities below a certain energy level. That can be a very powerful way of investigating convergence results. Okay. The second way, the second way. Oh, it's been a long day. The second thing I want to say is a different take on the setting. So this is called the exterior problem. I like this one. So the exterior problem is just the parallel lines, but instead of having the curve on the sort of inside, like this is the interior problem. And it's called interior, but of course it could, you know, go like this, not with our curvature condition, but the actual setting. The exterior problem is when you have double hooked curves, like that. And I think this is quite interesting because there's no equilibrium with this boundary conditions. So this is expected to converge to a singularity. So this is expected to be quite bad in its behavior. So why do I care about it at all? Because I think that if you have, let's say that you're close to this kind of configuration where you have sort of two semicircular caps on a straight line, glued together appropriately, then you would be close to the curvature of a circle, with initial data close to, close to us, so close to this. In what sense? I really am talking still about the same quantity, L times K in L2. And now on a circle, you know, let's say you have a circle of, this quantity is scale invariant. You know, if you make circles bigger or smaller, it's the same number. So if you have a circle of radius 1, then the length, circumference, is 2 pi. The curvature is 1. So this is just 2 pi times 2 pi. It's 4 pi squared. So this should be 4 pi squared plus something. So I'm going to let, for this second problem, I would let the delta be as small as you like because the conclusion is very tricky. So the conclusion is that this should converge in C0, but not in CL, where L is bigger than 1, to the straight line. Right, so I'll just grab this. Get rid of this guy, and then draw a straight line, like that. Now, what does that mean? I just mean that, so the end circles are going to shrink down, and the straight line is not going to do much, but move up. And so what will happen is that you'll have these little hooks on either boundary point, which will be singularities. And that should happen in finite time, which will make it quite tricky to analyze. Analyzing singularities for fourth order curvature flow have been quite a challenge recently, and so any kind of result of this nature would be really nice. What does it mean intuitively? Well, the thing that could happen which would make this result false is the following. So if you zoom in, if you zoom in on one of the boundary points, like let's make it really big, then you've got something like this. If this is just sort of shrinking like that, that is the good behavior. So what's happening is as this line is moving up, this loop is getting smaller. And its, leftmost point is moving inward. That's the good behavior. This is really what that sort of conjecture is saying. The bad behavior would be the following. I'll just draw it in a different color, maybe blue. So start off with the same kind of curve, but then as it moves up, it gets thinner. I don't know if you can see this. It gets thinner, but it doesn't get smaller. Maybe you can see it better now. Okay, and then so in the limit, what it would do is it would actually, it could still converge to a point, but it does so in a, let's say, a type 2 way, in a bad way. This would be collapsing. This is kind of a collapsing because you're losing a dimension. Whereas if it's more regular and if the cap is shrinking at the same time, similar to the movement of the line going upwards, then it would not be collapsing. So this kind of conjecture that I've made here is something like no collapsing, at least in this situation and in this sense. Okay, that's it, guys. It was a long one to finish, but I tell ya, it's been a bit of a marathon getting through these, and so if you got through them as well, then I thank you for your attention and for your time. But that's it. That's it from me. I hope you had fun. I hope you learned something. But in any case, take care of yourself. I think wash your hands. We're still washing hands. And I'll see you around. Okay. Peace.